Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Fourier transform, examples of Fourier transforms related to trigonometric functions, Gaussian wave function, and finite wave trains. Let's begin. We know the complex Fourier integral that is represented as the function f of x 1 by 2 pi integration over minus infinity to plus infinity, integration over minus infinity to plus infinity, e to the power I omega x minus t f of t dt d omega. We separate the two integrals, the double integration, further retain 1 by 2 pi integration over minus infinity to plus infinity e to the power I omega x d omega, integration over minus infinity to plus infinity f of t e to the power minus I omega t dt. Or f of x is equal to 1 by under root of 2 pi integration of minus infinity to plus infinity 1 by under root of 2 pi 1 divided by under root of 2 pi 1 divided by under root of 2 pi. These two multiplication results 1 by 2 pi. For the symmetry purpose, I use 1 divided by under root of 2 pi instead of 1 by 2 pi. Integration over minus infinity to plus infinity f of t e to the power minus I omega t dt. E to the power I omega x d omega. Let me substitute the integral 1 by under root 2 pi integration over minus infinity to plus infinity f of t e to the power minus I omega t dt is equal to f of omega. That equation can be changed to the form equation 1 written as the function f of x is equal to 1 by under root 2 pi integration over minus infinity to plus infinity e to the power I omega x. Instead of that integral we substitute f of omega d omega. Here the function f of omega that is equal to 1 by under root 2 pi integration over minus infinity to plus infinity f of t e to the power minus I omega t dt is called Fourier transform of the function f of t. Fourier transform of that function f of t, that is Fourier transform of the function f of t, which is equal to f of omega is equal to 1 by under root of 2 pi integration over minus infinity to plus infinity f of t e to the power minus I omega t dt, and the Fourier transform of the function f of t. Here f of t is called inverse transform, Fourier inverse transform of f of omega, that is Fourier transform of f of t, f of omega, and f of t is called the Fourier inverse transform of f of omega. The Fourier transform f of omega and inverse Fourier transform of f of omega are known as the Fourier transform pairs. Now we have to calculate for Fourier sine and cosine transforms. That is the example in case of trigonometric functions, how the Fourier transform is calculated. Fourier sine and cosine transforms. First, Fourier cosine integral. The Fourier cosine integral is given as f of x is equal to 2 by pi integration over 0 to infinity f of t cos omega t dt cos omega x d omega, which is equal to under root of 2 pi integration over 0 to infinity under root of 2 by pi. Instead of 2 by pi we use under root of 2 by pi as for symmetry purpose, as we previously used under root of 1 by under root of 2 pi. Same thing we introduced to evaluate Fourier sine and cosine transforms. Integration over 0 to infinity f of t cos omega t dt cos omega x d omega. Same thing, let us put f c omega is equal to that integral portion, integration over 0 to infinity f of t cos omega t dt. Then that expression of f of x will be 2 by pi under root integration of 0 to infinity f of c omega cos omega x d omega. Here that portion f of c of omega, which is equal to 2 by pi under root integration over 0 to infinity f of t cos omega t dt, is called Fourier cosine transform. Fourier cosine transform, or that is infinite series, so we call it as infinite Fourier cosine transform. Infinite Fourier cosine transform. Fourier cosine transform or infinite Fourier cosine transform. Similarly, that function f of x is said to be the inverse Fourier cosine transform of that function. Next, Fourier sine transform. In similar manner, you have to show. Similarly, the Fourier integral, the Fourier sine integral is given as the function f of x, which is equal to 2 by pi integration over 0 to infinity integration over 0 to infinity f of t sine omega t dt sine omega x d omega. Again introduce 2 by pi under root integration over 0 to infinity integration over 0 to infinity 2 by pi under root integration over 0 to infinity f of t sin omega t dt sin omega x d omega. There will be no such change. Let us put that integral as f of s omega 2 by pi under root integration over 0 to infinity f of t sin omega t dt. Then the given function f of x which is equal to 2 by pi under root integration over 0 to infinity that changes to f of s omega sin omega x d omega. Here f of s omega which is 2 by pi under root integration over 0 to infinity f of t sin omega t dt dt is called Fourier sine transform or infinite Fourier sine transform. F of s omega, that is the Fourier sine transform or infinite Fourier sine transform. So Fourier transform for trigonometric functions will be calculated like Fourier sine and cosine transform. That one is Fourier cosine transform, that one is Fourier sine transform for infinite conditions. Next, examples related to Fourier transform as Gaussian distribution function and finite wave train function. In these two functions we have to evaluate Fourier transform. Example, find the Fourier transform of the Gaussian distribution function f of t that is given as n into e to the power minus a t square, whereas a greater than 0, which one is positive, and n and a both are constants. That is Gaussian distribution function. The solution: from the definition of Fourier transform of function, f of t, we know Fourier transform of f of t which is equal to f of omega, that is equal to 1 by under root of 2 pi minus infinity to plus infinity the function f of t e to the power minus I omega t dt. Same thing, in place of f of t we use the Gaussian distribution function, that is Fourier transform f of t, which one is n a to the power e to the power minus a t square is equal to, instead of f of t we use that function value 1 by 2 pi integration over minus infinity to plus infinity n e to the power minus a t square e to the power minus I omega t dt, which is equal to n constant to outside 2 pi integration over minus infinity to plus infinity e to the power minus a, as common we have t square plus I omega t divided by a dt, which is equal to n divided by under root of 2 pi integration over minus infinity to plus infinity e to the power minus a. Here I add and subtract a term, that is t square plus I omega t by a. I add the term I omega divided by 2a square and subtract the same term I omega divided by 2a square. There will be no such change into dt is equal to n by under root of 2 pi integration of minus infinity to plus infinity e to the power minus a. Here t square plus 2 into t into I omega divided by 2a plus I omega divided by 2a whole square, one term, and minus a is multiplied to that term, so it will be e to the power minus a into e to the power minus expanding the square as I square omega square divided by 4a square to dt. Here we can use a plus b whole square formula, that is equal to n by under root of 2 pi integration over minus infinity to plus infinity e to the power minus a t plus I omega divided by 2a whole square into e to the power minus omega square divided by 4a to dt, e to the power minus a into e to the power something I square is equal to minus 1 minus minus plus 1a cancel out. Here there will be no such term of t, that term treated as constant, that constant term to that of outside we have n divided by under root of 2 pi e to the power minus omega square divided by 4a integration over minus infinity to plus infinity e to the power minus a whole into t plus I omega divided by 2a whole square dt. How to solve that kind of integration? So we have to substitute let us substitute t plus I omega divided by 2a is equal to y, which implies differentiating dt will be dy, another term as constant, there will be 0. Then the Fourier transform of that given function, which one is f of w. Therefore Fourier transform of n e to the power minus a t square is equal to n divided by under root of 2 pi e to the power minus omega square by 4a integration over minus infinity to plus infinity e to the power minus a y square dy. The substitution we introduce, or Fourier transform of that given function, that is f of w, f of omega, Fourier transform n by under root of 2 pi e to the power minus omega square by 4a, that integral is evaluated as pi by a under root. As we study the standard integration, here the standard integration results as pi by a under root. Also use the gamma function, we can estimate or evaluate that kind of definite integrals, which is equal to n 2 pi e to the power minus omega square divided by 4a. That is the Fourier transform of the Gaussian distribution function as f of t is equal to n into e to the power minus a t square. Finally, we write f of omega n divided by 2 pi e to the power minus omega square by 4a, which one is the required Fourier transform of the given Gaussian distribution function. Next, example of Fourier transform for finite wave train. The function which specified by the finite wave train function as f of t is equal to sin omega naught t, whereas magnitude of t less than equal to n pi divided by omega naught, and the function will be 0 when magnitude of t is greater than is equal to magnitude of t is greater than that n pi divided by omega naught. Fourier transform solution: Fourier sine transform, Fourier sine transform of the function f of t is given by Fourier transform as sine transform of the function f of t, which is Fourier sine transform f of s of omega, that is 2 by pi under root integration over 0 to infinity f of t sine omega t dt. That is the expression for Fourier sine transform. Just values are put it. Now the limit of integration we can change from 0 to t and t to infinity. 2 by pi under root integration limit change to 0 to t f of t sin omega t dt plus t to infinity f of t sin omega t dt. As limit from 0 to infinity, we change it from 0 to 2 t and t to infinity is equal to 2 by pi under root. Here from 0 to t, the value of that t, the function will be sin omega naught t. From 0 to t, from 0 to t, place of f of t we use sin omega naught t sin omega t dt plus from t to infinity that function will be 0. From t to infinity that function will be 0 sin omega t dt. Therefore, that integral results as 0. So, contribution only due to the first integral, and the limit 0 to t as n pi by omega naught. So, 2 by pi under root integration from 0 to n pi by omega naught sin omega naught t into sin omega t dt. Here we use the formula of 2 sin a sin b formula, that is cos of a minus b minus cos of a plus b divided by 2. That formula is used here. So 2 by pi under root, we introduce to use that formula 1 by 2 integration from 0 to n pi by omega naught cos a minus b omega minus omega naught minus omega t dt minus half 0 to n pi by omega naught cos of omega naught plus omega t dt. I just separate these two terms. Use the trigonometric rule, sin A into sin B formula. These two integrals now evaluated by taking the upper limit and lower limit. So 2 by pi under root, that integration results sin omega naught minus omega t divided by 2 omega naught minus omega as limit from 0 to n pi by omega naught minus here sin omega naught plus omega t, its integration results 2 omega naught plus omega limit from 0 to n pi by omega naught. Therefore 2 by pi under root sin omega naught minus omega n pi by omega naught in place of t using upper limit minus lower limit 2 omega naught minus omega minus sin omega naught plus omega instead of t n pi by omega naught divided by 2 omega naught plus omega. That is the required result for the Fourier sine transform of the given finite wave train equation. In this way, there are two examples related to Fourier transformation as Gaussian distribution function, its Fourier transformation, and finite wave train specified function as its sine Fourier transformation. The Fourier integral, as we write, that is the representation of Dirac delta function as a Fourier integral. How a Dirac delta function is written just like Fourier integrals. As we know, the Fourier integral of f of x is represented by Fourier integral representation f of x is equal to 1 by 2 pi integration over minus infinity to plus infinity e to the power I omega x d omega, that is the complex form, minus infinity to plus infinity f of t e to the power I omega t dt. Equation number 1. Let we reversing the order, then the integration can be written as or we say by reversing the order of integration, we write it as f of x is equal to integration over minus infinity to plus infinity f of t 1 by 2 pi integration over minus infinity to plus infinity e to the power I omega t minus x d omega dt. It is equation number 2. Now, from the property of Dirac delta function, we use a formula, but we know that useful property of Dirac delta function is given by f of x is equal to integration over minus infinity to plus infinity f of t Dirac delta function delta of t minus x dt. Equation number 3. Let we compare these two equations, equation number 2 and equation number 3. So, the Dirac delta function can be comparable to that integral. Now, comparing equation 2 and 3, comparing equation 2 and 3, we get delta of t minus x is equal to 1 by 2 pi integration over minus infinity to plus infinity e to the power I omega t minus x d omega. That part is same as that integral. That equation this equation is the representation of Dirac delta function, Dirac delta function as a Fourier integral. Dirac delta function as a Fourier integral. Let us put x is equal to 0. Putting x is equal to 0, we have del of t is equal to 1 by 2 pi integration over minus infinity to plus infinity e to the power I omega as t minus 0 d omega. Here t minus 0 as t. So, delta of t is equal to 1 divided by 2 pi integration over minus infinity plus infinity e to the power I omega t d omega. In this way, we represent Dirac delta function as a Fourier integral. The representation of Dirac delta function as Fourier integral. Dirac delta function as Fourier integral. So, with the help of this video lecture, you understand the concept of Fourier transforms, Fourier transform of a given function, Fourier sine and cosine transforms, Fourier cosine transform, that one is Fourier sine transforms. Examples of Fourier transforms for Gaussian distribution function and finite wavetrain function. Representation of Dirac delta function as a Fourier integral. So, with this useful and informative notes, let me wind up this session. Thank you.